So chapter 4 is called Antiderivatives and Indefinite Integration. Antiderivatives almost sounds kind of like a political movement too, right? People with picket signs, right? No more derivatives. Down with derivatives. Antiderivatives. But it's not. We are going to be actually undoing derivatives. That's what we mean by antiderivatives. We're undoing derivatives, or we're going backwards. We're going to be doing the inverse, really. The inverse of differentiation. So in this case, we're going to be starting with the derivative, and we're going to want to know, what was there first, so that when we took the derivative of it, we have what we currently have, right? So we're going backwards, and going backwards is always a lot more fun, if not more challenging, right? And indefinite integration. It turns out that indefinite integration and antidifferentiation are mathematical synonyms. It involves the exact same procedure, it's just in a slightly different form presented to you, okay? So let's go ahead and jump in here and read what it says. It says, suppose we have a function, big F, like Big Frank, not little f, whose derivative is given by the following. Big F prime is called little f, and it equals x squared. From your experience with finding derivatives, what might you say big F of x is? Or what was big F originally? 1/3 x cubed. Wow, how'd you get that so fast? Oh, he took the class last year. You didn't pass last year, huh? That's why you're retaking it? Yeah, okay. Well, here's what I would know. I don't know where you got the 1/3. That seems like kind of an arbitrary witchcraft thing to me. But I would agree with you that if I took the derivative and got an x squared function, then I would pretty easily determine that the function that came before the x squared, prior to differentiating, had to be a cubic function, right? Because I know when I take the derivative using the power rule, I multiply, and the last thing I do is subtract. And so if the last thing I'm doing is subtract, when I'm going backwards, the first thing I should do is add. So I know it had to come from a cubic. So I would use this as my crude primitive guess. I'm going to guess that it was originally x cubed. Now, the nice thing about anti-differentiating is you're trying to predict what you started with. You can actually think of it as a guess, check, revise method because you know how to check, right? Because we just studied how to go forward. So let me check by taking the derivative of both sides. So the left side becomes big F, which we've also named up above as little f, and the derivative of x cubed is 3x squared. And I compare it to what I'm supposed to have, and I'm like, oh, told you I'd get the x squared part, but it looks like I'm off by a 3. Right? I have an unwanted 3 factor. So all I have to do now, since I guessed, I checked, I just have to come back and revise. So here's my revision. I still think it's going to be an x cubed, but I want to have something sitting in front of x cubed that is going to neutralize the unwanted factor of 3, just like I take antacids before I go to a Mexican dinner feast, right? I neutralize the antacid or the acid that is about to come with antiacid, right? So what factor then could we have here in front of the x cubed to neutralize an unwanted 3 and call it a 1? A third, right? If you ever have an unwanted factor, your revision just has to have the reciprocal of that unwanted numeric factor, and then it'll work. So now we could check again. This is what Colin came up with on his own a little while ago. Now if I took the derivative, 3 times a third is 1, and that's good, x squared. So this is what we call an antiderivative. It's an antiderivative of f of x equals x squared. Now is an a definite article or an indefinite article? Yeah, it's an indefinite article. A definite article would be the antiderivative. So the word "and" implies that there might be other antiderivatives. How in the heck is that going to happen? Oh, okay, there he goes again. 1/3 x cubed. What did you say? Something about a constant? Like plus what? 5? Sí, yeah, we're speaking Spanish now. Okay. 1/3 x cubed plus 5. If I take its derivative, I get x squared plus 0. Nada. Muy bien, muy bien. So in general, when you take the derivative, you lose information, right? You lose constants. So when you're going backwards, you can make the allowance that any constant could have been there. And it just so kind of very coincidentally turns out that we call that unknown constant the same word for yes in Espanol phonetically. Sí, right. So I don't know if you meant that, Colin, but that's just a strange coincidence. That he wanted to talk Spanish and we call that sí at the same time. This is what we call the definite article antiderivative of bless you, where bless you equals f of x equals x squared. It's the antiderivative. In fact, we call this really the general antiderivative as well. The general antiderivative. Now, it could be that c is 0, it could be that c is 5, it could be that c is 100. We don't know. We just make the allowance that there could have been something there. All right, so let's go ahead and define. A function big F is called an antiderivative of a little function f on some interval if the derivative of big F is equal to little f. So we kind of have this new notation. Normally when we start with a function, we start with f, and then we go by taking the derivative to get f prime. We take the derivative again to get f double prime. Now we need to have some terminology for going backwards one layer. And if you go backwards by anti-differentiating, we come up with the notation of big F. Now, we really don't have anything that goes back from big F. If you wanted to, I guess you could call it like script letter F. Yeah, or bigger F, right. Yeah. So typically, we're going to be throwing you a function, f of x. And so the antiderivative we're going to call big F. If we throw you little g, the antiderivative could be called big G. It still shows that they're related somehow, but that's how it takes its place in this derivative sequence. Okay, so here are some more antiderivatives, by the way, of x squared. 1/3 x cubed, 1/3 x cubed plus 3, 1/3 x cubed minus 2. That's a nice one. The minus 2, that's a real nice one. I didn't think about that one. That's a good one. Yeah, and they're all called antiderivatives because they all have the same derivative, x squared. So if you have more than one antiderivative to a function, they're only going to differ by the constant, right, by a plus c. And what would that do to the graphs of the antiderivatives? What does a plus c do to the graph of functions if that's the only thing they differ from? Yes. Exactly what you all said at the same time. I'd pick a couple of pieces of that. Vertical shifts of each other? Maybe I didn't hear that. They're all vertical shifts of each other, right? So if you notice, these all look like cubic functions, and the only difference is one is slid up and one is slid down, which, you know what, I've never done this, but we could do this now with Notability, right? Trace over one and then just, there they are. How many antiderivatives are there then? Infinitely many, yeah. Now remember, we've looked at this already this year where we sketched the graph of derivatives from functions. And in this case, if you were to do that, at this value of x right here, the slope would be whatever the slope of that line is, which would be the same as the slope of that line, which is the same as the slope of that line. So notice all of these functions graphically still have the same derivative because we're looking at the slopes of that graph, not at the y values of that graph. And so there are infinitely many antiderivatives for any given function. And that's good to have infinitely many, right? Because that increases your chances of coming up with one of them correctly a lot better. You just need one out of infinity. Okay, let's try it out. Example 1, find the general antiderivatives of each of the following using your knowledge of how to find derivatives. Now again, we're going to practice both the notation and the actual process. So what would be then the left side if we took the antiderivative of big F? Or the little f, sorry. God, gave it away. Pretend you didn't hear that. Big F, thank you. Big F of x. And on the right-hand side, what's the antiderivative of 2x? X squared plus c. Now let's check real quick. What's the derivative of x squared? 2x. Good. So the antiderivative of 2x is x squared plus c. Plus c. Good. We started with the degree 1. We ended up with degree 2. Nice. How'd you know to take the 2 away? I'm curious. Well, how'd you know that it wasn't 2x squared? Oh, because if you take the derivative, you get a 4x. Okay, so then you should have nothing there. So you get the 2. Okay, y'all are smart. All right, let's try this one. Little f prime equals x. What's the antiderivative of little f? Prime. Little f, right? We go back one and we got little f. And hang on, don't tell me. It's x to the first now, so I know it's going to be an x squared. And so now 2 times whatever's in the front better equal the coefficient of 1. So I'm going to guess 1/2. Am I right? So 1/2 x squared plus c. Yeah. All right, here, let's check. I want to check. So the derivative of little f is f prime. That looks good. And we are going to multiply. So we get 1/2 times 2. That's multiplication. And we do that first. And then we get x to the 2 minus 1. That's the second thing we do. That's subtraction. And then the c goes to 0. So if I simplify all that mess, I do get x. So it worked. Now, because we are actually undoing derivatives, right? The antiderivative is the inverse. We know how to find inverse functions, right? If I took a random number, multiplied it by 4, and then subtracted 3 from it, and I told you that number, you can get back to my original number pretty easily, right? All you'd have to do is add 3 and then divide by 4. You do the inverse operations in the reverse order. That's the same thing we could do with the power rule in reverse. Let's say we start with, not a highlighter, f prime equals a times x to the nth power. All right, so going backwards now, we use the power rule in reverse. Instead of multiplying and then subtracting, we would do what? Add and then divide. Okay, let's see if that works. So I'm going to first of all add 1 to my old exponent of n to get n plus 1. And then I'm going to divide by that new exponent, and I get a over n plus 1. And then I put a plus c for the constant. Does that work? Well, let's check. What would be the derivative of the left side? F prime, that's good. If I multiply now, what happens with my n plus 1s? They divide out, and I'm left with ax to the now n plus 1 minus 1 is n. There you go. Congratulations. There is the power rule for anti-differentiation. All right, so let's come back and look at it in that respect. You got it with x squared plus c intuitively. But let's use the power rule. Big F would be, all right? So the 2 is a constant multiple. I'm going to say he goes along for the ride. I'm going to leave a little space. I add 1 to the current exponent to get 2, and then I'm going to divide by 2. But you know what? Dividing by 2 is the same as multiplying by what? 1/2. So if I want to divide by the new exponent, that's equivalent to multiplying by its reciprocal. And then, of course, I'll put plus c. And now if I simplify the 2 that was there to begin with and the 1/2 that I added, the reciprocal of my new power, what happens to those two? They divide out to give you 1. Yeah. So it appears that this new power rule works. And for things that aren't as intuitive, it gives us that algorithm. Add 1, and then instead of dividing by the new exponent, I would say, let's go ahead and just multiply by its reciprocal. It's the same thing. So let's try this one out. Letter C. Big F prime of x equals 2/3 x to the 4/7. The left side becomes big F of x. And if you were trying to find the antiderivative of this one intuitively, you'd be like, oh boy. It's not as easy as calling a 2x an x squared. But guess what rule will work now? The power rule. If you have a constant that's there in the beginning, just assume that he's going to be there all the way through the problem. In fact, I call him a rider. He's like a guy you picked up on the road and you drive a truck. He's just in the back of the truck. You don't even know he's there, right? Just you're giving a ride to some guy. So he's there in the original problem. He's going to be there in the end. And now we focus on the variable part. By the way, that worked for derivatives too, remember? When we took derivatives, constants went along for the ride. So let's focus on that. Leave a little space. We add and then divide. Instead of multiply and subtract, we add and then divide. We add and then divide. So what is the new exponent? Well, it's 4/7 plus 1, which is 11/7. Now, you could divide by 11/7, but then you're going to have a complex fraction. Yucky, yucky, gross, gross, right? So that's why I say instead of dividing by the 11/7, we'll just multiply by its 7/11, right? And then plus C. Tie it off with the plus C. It's like a cherry on top, but not on the top. It's off to the side, plus a cherry. Sure, whatever. And now, just like when you took the derivative and you let constants go along for the ride, you can now combine any constant that's left. This is now going to be another constant I'm going to call the rule constant. We got the rider, the guy that was there in the beginning. I'll relabel him down here. And then using the new rule, add and multiply by the reciprocal of the new exponent, we get another coefficient. And now we can simplify those. Nothing divides out, so you get 14/33 x to the 11/7, and don't forget the plus c. So I doubt that you could have come up with 14/33 x to the 11/7 very, very quickly if you were just relying on your intuition, right? So now we can systematically do it. And you better love this power rule for antidifferentiation because it's like the only rule out there. Antiderivatives themselves don't have many rules, like product rule, quotient rule, chain rule. It's like the only one, really. So anyway, use it when you can. All right, over here. Lil g prime of x is 1 over x squared. Very good. Just like if we were going to be finding the derivative using the power rule, we're going to have to write everything of the same form, a times x to the n. So before you take the antiderivative, you're going to write 1 over x squared as x to the negative 2th power. Now we'll take the antiderivative of both sides. What's the antiderivative of lil g prime? Lil g, right? Just lil g of x. And here we go. Leave a little space. We add and then divide. Add, then divide. Add, then divide. What's negative 2 plus 1? Negative 1. And then you divide by the new exponent, but dividing by negative 1 is the same as multiplying by negative 1. So you can put a negative 1 in front, and then we tie it off with the what? Plus c. Don't forget the plus c. You will lose points every time you're finding an antiderivative and you don't put plus c. You don't want to lose those points. You don't want to become a statistic. That is a totally different class. Okay? So now we'll just clean this up, and we get negative 1 over x plus c. Yay. Yay. And now if you're not sure if that's right, you're like, it doesn't feel right. What can you do? Check. Yeah, let's check from this version. We'll check. We'll check, okay? The derivative of g is g prime. Good. And now we'll check. Okay, so the power rule. Negative 1 times negative 1 is positive 1. And then we subtract negative 1 to get negative 2, and c goes to 0. And that's the same as 1 over x squared. And yeah, we're so good now we don't really have to check unless we want to show off. All right. Hey, Mom, look what I can do. All right, dy dx equals cosine x. So what's the antiderivative of the left side? Y. Good. And over here, we just add and divide, right? So the current exponent is 1, we get 2, and then we divide by 2, which we know is the same as multiplying by a half, plus c, right? What? How about no? What do you mean no? Watch, let's check. Let's check. If I take the derivative, I get y prime or dy dt, and oh boy, it looks like I have the chain rule over here now. Where did that come from? 2 times a half is 1, cosine of x to the first, times the derivative of cosine, which is negative sine, plus c. Okay, you know what? I pick up what I want, but I pick up an unwanted negative sine of x. So let's just go back and revise it. If I have an unwanted negative sine of x, then maybe all I have to do is revise it by putting a negative 1 over sine of x as a correction. How does that work? If you want to check again, guess what you're going to have to do now? A product rule. Oh, okay, cool. So here's a lesson that we learned right now. You cannot revise with a variable. You cannot make a correction of a variable. You can only correct an unwanted constant multiple, okay? Only a constant multiple. Because remember, when you take the derivative of those, they go along for the ride. If you correct it with a variable, now you're changing the original problem into like a product rule or something. So, yeah, not everything is going to be a power rule in reverse, is it? No. Just like not every derivative rule was a power rule. Now, we don't have rules necessarily, but at some point, we are so good with taking derivatives, we can find antiderivatives pretty intuitively. What's the antiderivative of cosine? It's sine of x. And then, of course, plus c. And now if you check, what's the derivative of sine? Cosine. And the derivative of a constant? 0. Yeah. So I wouldn't even call this the cosine rule for antidifferentiation, but if you want to, you can. Not everything's a power rule. You ask yourself when you're facing this, what do I take the derivative of to get cosine of x? And the answer is sine of x. Okay, so let's go ahead and look at a table of antiderivative formulas. There's not many. The first row, if you have an unknown constant little c times a function little f, then the antiderivative is still little c times big F plus the constant c. So constant multiples go along for the ride. That's what this says. If you have a constant in the beginning, it's going to be there in your final answer. You can simplify after you come up with your antiderivative by combining all of your constants in the front. But it doesn't have to factor into your antiderivative process. Here's a property. It's not a rule, it's a property. If you want to find the antiderivative of multiple terms, like f plus or minus c plus or minus h, just like with derivatives, you can tackle each term separately, okay? Tackle, each term separately. They become like their own miniature problems. So the antiderivative of little f is big F, plus or minus. The antiderivative of little g is big G. You just remember to add plus c. All right, here is the power rule. X to the n when n isn't equal to negative 1. You add 1 to get x to the n plus 1, and then you either divide by the new exponent or you multiply by the reciprocal. And then you tie it off with a plus c. Now it says when x is not negative 1. I'm kind of curious now. So when told not to do something, guess what? We look around, see if no one's looking, and then we do it, right? So why doesn't it work? If I have f prime equals x to the negative first, then little f would be, let's see, right? By the power rule. We add and then divide. We add and then divide. What's negative 1 plus 1? 0. And then I'll divide by 0 or multiply by its reciprocal. Ha-ha. I got around dividing by 0. No, you didn't. You're still dividing by 0 or multiplying by the reciprocal of 0. It's the same thing. Yeah, it doesn't work, right? Because we can't divide by 0 because our name is not Newton or Chuck Norris. So dang it. Okay. Are there any other values on the exponent that don't work besides negative 1? No, all the other values work because 0 is the only value we can't divide by. Then negative 1 is the only number in the world that when you add 1 to it gives you that number 0. That's taboo. So the power rule works for every single exponent in the whole world except negative 1. It works for fractions, it works for non-fractions, it works for positives, negatives, it even works for 0. It just doesn't work for negative 1. So what happens if the exponent is negative 1? Are we out of luck? No. Go to the next row. What's another name for x to the negative first? 1 over x. If you have 1 over x, the power rule doesn't work, but guess what? You take the derivative of to get 1 over x. Natural log of x. Yeah. Now notice because we're starting with this, what's the domain of the function 1 over x? Everything except what? 0. So when we take the antiderivative, which we know is going to be a natural log, we add absolute values to it so that we can preserve the domain of the original function, right? We can only take logs of positive numbers, but because we're starting with 1 over x, we want to be able to use negative numbers, you have to add the absolute values to the antiderivative. And of course it works. When we check, what's the derivative of the natural log of the absolute value of x? The absolute values go away and we get 1 over x. So when the power rule fails to work in that single case, when you have something raised to the negative first power, or you have 1 over something to the positive first power, when the power rule fails in that singular case, who comes then to the rescue? Natural log. Good. Don't forget to put absolute values around it, plus c. All right, what's the antiderivative of e to the x? E to the x, it's antiderivative. E to the x plus c, very good. E to the x plus c. It's its own grandpa, right? If you are your own grandpa, you are also your own grandson. Makes sense. I wonder if there's a song for that. I'm my own grandson. Probably not. Grandsons are too early to write sophisticated songs. Too young. Antiderivative cosine. Sine of x plus c. Good. Antiderivative of sine. Negative cosine? Oh, yeah. So what's that negative doing there? He's chilling. He's actually what I call the correction, right? Because the derivative of cosine generates a negative sign, I don't want there to be a negative there because I'm starting with positive sign. So I can have a negative 1 essentially in front to neutralize then the unwanted negative that comes off the cosine. So yes, it is negative cosine. plus c. What's the antiderivative of secant squared? Tangent, right? So because we know the derivative of tangent is secant squared, the antiderivative of secant squared is tangent. What's the antiderivative of cosecant squared? Right, negative cotangent. And once again, plus c, we have that -1 correction so that it gets rid of the unwanted negative. What's the antiderivative of secant tangent? Secant. So these aren't really rules. These are just going through our derivative rules in reverse, right? Because the derivative of secant is secant tangent, the antiderivative of secant tangent is secant, pause, plus c. All right, what's the antiderivative of cosecant cotangent, period? Negative cosecant plus c, exclamation point. I don't know. Yeah, upgrade. All right, how about this rascal? That is an ugly thing. How are we supposed to know the antiderivative of that is? Yeah, because we know that it's the derivative of sine to the negative first, inverse sine we call it, or arc sine. So now the antiderivative of 1 over the square root of 1 minus x squared is inverse sine of x plus c. What about the antiderivative of 1 over 1 plus x squared? Inverse tangent plus c. And what's the antiderivative of this ugly dude? Inverse secant. Absolute values. There's another place where we add them. This one doesn't show up that often. But remember, when we take the derivative, we have them there when we take the derivative. When we find the antiderivative, we put it around the ratio. Okay? So again, if you know all of your derivatives going forward, you already have this list down, now including the power rule in reverse. So maybe you go back and review all your derivatives. All right, let's try it out. Example 2. Find all the functions g, little g, such that g prime is equal to this. Holy moly smokers. Wow. Well, let's think about what we had to do in the beginning when all we had for the derivative was the power rule. If you had something like this, 3 terms over a single term, what did we have to do? Yeah, move it to the top and distribute it, or split it up, right? That's probably a little bit easier. Put each term over the denominator. We'll have to do the same thing here. So a little bit of rearranging of some terms so we can work with it. G prime of x, 4 sine of x looks good. Now if I split it up, I get 2x to the 4th over x. That's going to be plus 2x cubed minus x to the 1/2 divided by x is x to the negative 1/2. Good. And then plus x over x is 1. Now in the next one, you got to be careful. There's a negative out front, so we're going to have to distribute the negative. So we get negative 7x cosecant squared over x is just negative 7 cosecant squared of x. And then we're left with negative 1 over x, which if you want to write it as x to the negative first, or leave it as negative 1 over x. It's up to you. If you put it as x to the negative first, when you come try the power rule, you're going to get a 0, and you're going to divide by 0, and you're like, oh, silly me. Wherefore art thou, natural log? Come save me. Okay? Or if you leave it as 1 over x, you're just like, I know that's the derivative of natural log of x. Whatever. All right, so now we're ready to go. On the left side, what's the antiderivative of lil g prime? Lil g, okay. And then the antiderivative of 4 sine of x. Well, let's see. I know it's going to be a cosine. So if you, again, guess, check, revise is a great strategy. If you're guessing 4 cosine of x and you quickly check, what would be the derivative of 4 cosine of x? Negative 4 sine of x. Do we want it to be, bless you, negative, bless you? No. So we have to have a Kleenex or a little negative 1 in front to neutralize the unwanted negative. So there it is. Plus, all right, 2x cubed. You're going to get real good at this, right? Leave a little space, the coefficient. Just don't even write it. Leave a little space. X to the 3rd becomes x to the 4th. And then times the 4th. Times the 4th. What was there to begin with? 2 times the 1/4 is 1/2. Now, if you could do that in one step, feel free. That's where you should be. Right now, for instructional purposes, I'll just kind of say constant multiples go along for the ride, and then we do the power rule. Add 1, multiply by the reciprocal. Minus, same thing here. X to the negative 1/2, when you add 1, becomes x to the positive 1/2, and then instead of dividing by 1/2, we'll multiply by its reciprocal 2. Plus, what's the antiderivative of 1? X. Very good. Because the derivative of x is 1, If you ever have an antiderivative of a constant, all you got to do is add an x behind it. And then now the antiderivative of -7. Well, -7 goes along for the ride. What's the antiderivative of cosecant squared? Negative cotangent. Good. So the fact that it's a negative cotangent makes this a positive cotangent of x right there. And again, if you're not sure if the sign is correct, guess, check, revise. If you're off by a constant multiple, whether it's a -1 or a -52 or whatever, you can put the reciprocal of the unwanted factor in the front. And then finally, finishing it off here, minus the natural log of absolute value of x. Good. And we're done, right? Plus c. Now we're done. Now we're done. Plus c. Okay, we'll stop right there for today. You got some antiderivative worksheets now waiting for you. Practice, practice, practice.